You know, some laws of physics just feel like they're carved in stone, right? Like they're absolute and completely unbreakable. But what if I told you that one of the most basic rules, a rule about symmetry itself, was just shattered by a single brilliant experiment? Well, today we're unpacking that exact story.
It's a question that sounds like it's straight out of science fiction, doesn't it? Like, if you could make a perfect mirror image of our entire universe, would it behave in the exact same way? For the longest time, physicists would have said, yeah, of course. But, as we're about to find out, the universe has a few surprises up its sleeve.
All right, so here's how we're going to break this down. First, we'll look at this perfect mirror rule that everybody believed in. Then we'll dive into a really weird particle puzzle that just didn't make any sense. After that, we'll see the incredibly clever experiment that put it all to the test. And finally, we'll get into the shocking result and why it matters so much.
So, for decades, physicists had this really beautiful idea about how the universe worked. They were convinced it was fundamentally symmetrical, like a perfectly balanced equation. This concept, they called it parity conservation, was so intuitive, so neat, that it was basically treated as a core law of the cosmos.
Okay, so here's the main idea. Imagine you're watching a game of cosmic billiards. You see the balls hit, they scatter. They're following the laws of physics. Now, parity conservation says that if you were to watch a video of that same game, but reflected in a mirror, everything you see should still look completely normal. The mirrored game should still obey all the exact same rules as the real one.
And this rule seemed to work everywhere scientists looked. Gravity? Yep, it checked out. Electromagnetism? That worked too. The strong nuclear force that holds atomic nuclei together? Also symmetrical. But there was one force that hadn't really been put under the microscope. The weak force. That's the one that handles certain kinds of radioactive decay. At the time, nobody really thought it'd be any different. But a new puzzle was about to change everything.
So, this brings us to the 1950s. Physicists are finding this whole zoo of new particles and cosmic rays, and among them are two that look, well, weirdly familiar: theta and tau. They seemed harmless enough, but they were about to trigger a full-blown crisis in physics.
And this is where things just got bizarre. I mean, when scientists measured these two particles, they were identical twins. They had the same mass, the same lifetime, the same spin. By all accounts, they should have been the exact same particle. But, and this is a huge but, there was one critical difference: the way they decayed. The theta particle broke down into two smaller particles, giving it what's called an even parity. But the tau particle decayed into three, giving it an odd parity.
Now, if parity conservation was a true law of the universe, this was flat out impossible. It's like finding a person who is somehow both left-handed and right-handed at the exact same time. The physics community was totally stumped. There were only two possibilities. Either there were two completely different particles that were just miraculously identical in every other way, or one of the most fundamental laws of the universe was simply wrong. This was a huge problem.
And that's when the brilliant physicist Chien-Shiung Wu stepped in. She looked at this puzzle not as a crisis, but as a huge opportunity. Working with her colleagues, she designed this incredible experiment in 1956 to ask the universe a very direct question. Are you the same in the mirror, or do you actually have a preference?
The setup for this experiment was just genius. Okay, so first, to get a clear signal, they needed the atoms to be as still as possible. So they cooled a sample of cobalt-60 to almost absolute zero. We're talking unbelievably cold. Then they hit it with a powerful magnetic field to get all the atomic nuclei to spin in the exact same direction, kind of like a row of tiny, perfectly aligned spinning tops. Once everything was frozen and pointing the same way, they could finally watch and see where the electrons went when the atoms decayed.
This was the million-dollar question. If the universe really was symmetrical, if it had no built-in preference for left or right, then the electrons should have just shot out randomly in all directions. You'd expect an equal number to fly up with the spin as fly down against the spin. The result should have been perfectly, beautifully balanced.
Now, the conditions for this experiment were so insane that they could only keep it going for about 6 to 8 minutes at a time before the whole thing warmed up and the alignment was lost. But you know what? In those few precious minutes, the universe decided to tell its secret.
The result was immediate, and it was undeniable. The electrons were not flying off randomly, not even close. Instead, most of them were consistently being shot out in one single preferred direction. The perfect balance everyone expected? It just wasn't there.
So here's what they actually saw. Most of the electrons were flying out in the direction opposite to the spin of the nucleus. And here's the part that'll blow your mind. The mirror image of that event, where the spin is up and the electron is also emitted up, that version of reality, it just doesn't happen. The universe had picked a side. The real world and its mirror image were fundamentally different.
The conclusion was an absolute bombshell. A fundamental law of physics, something everyone assumed was true for all forces of nature, was broken. The weak force, it turns out, does not give a hoot about mirror symmetry. At its core, the universe can actually tell its left from its right.
So a major law of physics gets tossed out the window. What does that actually mean for us? Well, it fundamentally changes our entire picture of reality itself.
What this discovery showed us is that the universe has a kind of handedness, just like we have left and right hands. The weak force, you could say, is inherently left-handed. This immediately solved that whole theta-tau puzzle. It was just one particle all along, decaying in a way that didn't follow the old rules. But the biggest lesson here was for the scientists. No law is so sacred that it can't be questioned. Every single idea, no matter how elegant, has to face the music of experimental evidence.
So we now know we live in a universe that isn't perfectly balanced. Down at the subatomic level, where the weak force is in charge, there's a clear and obvious bias. This one experiment completely reshaped the standard model of particle physics and forced us to accept a much stranger and honestly, a much more interesting reality than we had ever imagined.
And that's what science is all about, isn't it? The story of parity conservation is this incredible reminder that our understanding of the universe is always a work in progress. It really makes you wonder, what other unbreakable laws are just sitting there, waiting for the right experiment to come along and shatter our view of everything all over again?